Welcome to Spectrum Perspectives, real talk with parents, professionals, and autism advocates, with your host, Cindy Gellermini.
Hi, everyone. This is Cindy with another episode of Spectrum Perspectives, and today I have Elizabeth Torres with me from Rutgers University. Hi, Elizabeth. Welcome to the show.
Hi, Cindy. Thank you for having me.
So I've been doing a series of interviews about spelling to communicate, talking to some parents and some professionals, and several people said that I needed to talk to you. So I don't know what you do exactly, but we're going to find out. And all I know is that you're at Rutgers, and I had interviewed Christopher Menente last year, and about the autism program there, and that's all I know. But I think what you do has nothing to do with what he does.
No, not at all. It's quite the opposite.
Yes. So tell me a little bit about you. First, I always like to start in the beginning. Tell me a little bit about your background and then how you got to where you are today, and then we'll talk about what you do now.
Yeah, so I'm by training an applied mathematician, and I was working on models of autonomous motor control for robots, and all the way back in the mid to late 1990s, I was working on artificial neural network models to control robotic arms and produce essentially the equations of motion to control, to model how the human brain controls the many degrees of freedom the body has. This is a fundamental problem in robotics, or anybody who wants to build an autonomous agent would have to do the mathematical modeling of the equations of motions and something called the kinematics of motion, which deals with the geometry of these very high dimensional spaces. And so that's what I was doing. I was just building models, testing empirically, which means you go and collect data from people in motion, naturally moving. And, so I was collecting data from athletes, high performance athletes, doing, the tennis serve, which is a very complex movement, and doing gymnastics. And then I came to boxing and karate and martial arts. And I was testing in my lab people from there were people from the lacrosse team at Rutgers. There were professional tennis players. There were gymnasts. There were ballet dancers. And the question that I had was, how does knowing and being proficient at the professional competitive level in one sport impact the learning of a new sport? And the new sports was martial arts. And so I had competitors in martial arts, boxers and kickboxers and so on. And I had all these other slew of people that were in other sports. And that was what I was doing back in 2009. And I had all these people wired up, and the movies are amazing, and you get avatars, and and I was doing the analysis, and I discovered that there were, even though in motor control and robotics and all of that, we study intentional movements, voluntary movements, goal-directed movements, I discovered a whole new class of movements that I coined spontaneous movements, because they have a particular signature, a particular characteristic that is very different from goal-directed movements. And turns out they're engaged in this learning process of transferring motor programs that you have in one sport to another sport and adapting them. And I thought, these are a fascinating class of movement, because nobody knows about them. People don't know they exist, because they fall beneath awareness. So all these professional athletes that are doing this stuff, like from 4 years of age, they don't even know they're doing this. So along the lines comes this girl that was in the lacrosse team and brings her brother, who was a 17-year-old autistic adolescent, to sit there with her, where they were going out to lunch, and she stopped by the lab to do the experiments. So I wired her up and everything, and we started. And I had the professional boxing athlete there, following the routines and so on, instructing her and so on. And she does her thing. And then I noticed that her brother is at the corner sitting. Not once he like looked at her, he was like there doing his gaming and video playing, whatever. And she said, Jimmy, you wanna try this? And he said, yep. And he stands up, we wire him up, and he does it from beginning to end without rehearsal. Like, we had to get this girl 4 times in the lab to get the whole fluid routine, to just practice. And he goes from beginning to end, and I have it in video. I mean, we were like, what? What? And he wanted to be, he when I asked him, and his whole thing is he wanted to be a designer, and he could draw perfectly. Like, drawing was like, he was gifted. And so I said, wow. So I go back to my analysis and so on, and I discovered that even though he did this perfectly in the space domain, in the temporal domain, there were and looking at the speed of the movement, the peak velocity of the movement, there was a very peculiar signature. And that signature was that the distribution, the probability distribution of these parameters was exponential, which is a special distribution that signals that the random process that you're performing is memoryless, and it's completely random. And it means that you're intaking all the information in the here and now, as opposed to having a process that is predictive, meaning that events in the past are predictive of events in the present, and events in the present are predictive of future events. And in the motor domain, this is very important, because with the complexity of what we do and the many degrees of freedom in the body, all the joints rotating and all the limbs translating and all of that, for the brain to control the synergies and so on, the timing is very important. And predicting ahead the time of the consequences of your actions is actually the ticket to solving the coordination and the control issue in such a complex agent, so that the agent is autonomous. Part of the autonomy of the agent comes from the fact that all of this information and prediction and so on is done for you. The brain is busy with other things then. The brain can afford to be learning other things and busy with other things. If you don't have this in place, then you have to do a lot of top-down monitoring of stuff that goes on automatically, just regularly, automatically, that the brain doesn't have a cognitive load having to think about all of this. And this, years later, so this was we're talking 2009, and this was a discovery, because we've never seen anything like this anywhere. And it's explained a lot about the way later on, after sampling thousands of individuals on the spectrum, the disconnect between the mental intent to move and the actual execution of the movement. Because the actual execution of the movement, to be in tandem with the mental intent, has to be timely, has to have this temporal information, and it has to be ahead of time, because there are delays. So every processing that we do is sensory processing, including the processing of the sensation of our own self-generated movements, which is a form of sensory input. It's called kinesthetic reafference. And it's contributed also by proprioception, and it contributes to the vestibular sense, so that we know where in a space our body is, all our body parts, and we can control it and balance, our gait and everything. So if you don't have this kind of predictive code that you're a step ahead to compensate for the delays in all the sensory processing, in all the sensory motor integration, and in all the sensory to motor and the motor to sensory transformations that need to occur, then your system is not entirely autonomous, because there is this disconnect. So you have to, instead of doing things autonomously and automatically, your brain has to spend a tremendous amount of time and effort on doing what everybody else's brain is doing automatically. So you're actually controlling all of that, which is a monumental feat. Like I cannot even imagine a person doing this, but we did imagine, we actually met the person who did this in the worst case scenario, which is when you lose entirely the proprioception of your body. And that rang a bell, because then it's like, that totally, when I saw that, and it's like, okay, there is a problem with the reaffirm code and the prediction. Who had that problem? Well, Ian Waterman, this man who lost his proprioception from the neck down because of a viral infection that killed the nerves that transmit information throughout the body to the brain and the spinal cord, the center. So the peripheral nervous system in the body, the central nervous system, the brain, the spinal cord. So this information goes through the spinal cord and then through the brain. And we have very sophisticated maps of space and time and everything to deal with this. And he lost it. And then he was able to sensory substitute with vision. So visually guiding all his movements, he was able to remap the entire body, proprioception, which he had lost, into a different domain. And so he moves. He was for years paralyzed. For years, he was in bed, he couldn't move. Because the movement, when we move, and we move in a coordinated manner and so on, the motor control is not given by outputting the muscles, the forces to tense the muscles up. That's not it. That only gets the information to the muscles. If you have good muscles, if you don't have low tone or low muscle tone, or you don't have spasticity and your reflexes have evolved proper and so on, your muscles will tense and you will get a posture, right? That's what that does. But that doesn't mean that you will move smoothly. To move smoothly, the same step, the next step needs to read out that information and bring it back to the brain, so that there is an error code between what you intended to do, that posture that you intended to do, and what you actually did. And that error code, it's minimized, it's optimized, so that eventually you do what you match exactly what you intended to do with what you actually physically do. And so this is like in a loop, right? So this is like in a time series that goes continuously over time. And you learn this, we learn this as babies. We learn this when we're neonates. You know, we start in the womb and we come out to the gravitational field here on Earth, and we adapt and we learn all these maps to then control our, by the 30th week, we already have anti-gravitational muscle movements that enables us to sustain the body and control emotion and reach and grasp. Okay, that we begin that process. It doesn't mature until 4 to 5 years of age. Takes a long time to mature. Gait the full body up against gravity, that takes even longer. That takes 8-9 years of age. So it's a very complex problem. If the brain has to pay attention to all of that, it has a big load. And that's what we discovered. That in autism, it's not that they cannot do it, they can do it, but it is a big cognitive load, a big effort, a big cognitive effort that their brain is devoting to all of this. And that has a price. And part of the price is that you need to support the body while the system builds these maps. You need that support. You need that physical, emotional support, because the body is in a constant state of uncertainty, right? Because when we have a code that is clear and is predictable, and we can predict the consequences of what we intended to do, even before we do it, we are very certain of what we're about to do. We don't have the anxiety, we don't have the uncertainty and the anxiety and the stress that this creates. So over the years, then we sample the entire body, the heart, the face, the entire body, and we realize that there is a huge difference. There's a huge gap that we need to help these kids. And it's not that they cannot do it. This is the beauty of it, that actually those spontaneous movements that I told you before about, that we discovered in this atlas, those are the ticket to doing it. But because they're beneath awareness, you don't see them with the naked eye. So you have to really look at it through the digital lens, and you will see these spontaneous movements. They start at conception. They come from central pattern generators. They adapt to become intentional, and they remain throughout life. As in these top athletes that were top in one sport, and they needed the spontaneous movements to remap to a new sport, and that helped them become proficient at the new sport. And it's just a human, that's the way our brain works.
Mm-hmm.
But so we discovered that the spontaneous movements are really something we can utilize to bridge the mental intent with the physical execution and help the body support the body.
What's an example of a spontaneous movement? What do you mean?
Yeah, so an example is, so when you go and you point to a letter on the letter board, all right, that's a goal directed, that is a deliberate voluntary movement to the target.
Mm-hmm.
But look at my hand, I go back. That's a spontaneous movement.
Oh, okay.
It connects the next movement,
Mm-hmm.
but it's beneath awareness. Now in the autistic system, it is on awareness, full awareness. They're full aware of that one and of that one. And so just like Ian Waterman, the man who lost his proprioception,
right,
he recoded it by vision. The kids might be recoding also by auditory. It's just that they're aware of it. And because they're aware of it, we can utilize them to then learn to predict the ones forward in an easier way.
mm-hmm.
Okay, so this is a closed loop, and they're coexistent with all the other movements, because these are segments that happen in every complex action. So in the tennis player, for example, when they were doing the tennis serve, these are also segmented into voluntary and spontaneous, the ones that they're not aware of. And if the tennis player, professional athlete, had a great serve, and I would say, hey, you're doing something really great with your wrist because the serve is fantastic, and I can see here in the data, I would disrupt transiently the good serve, because now he's paying attention to that movement that goes beneath awareness.
Mm-hmm.
And so now he's like completely, conscious of that. And then that disrupts, and that's kind of like what they call the jitter or whatever in golf. That's part of it, that the athletes then become aware of these spontaneous movements, and then they become intentional, and then that disrupts the whole flow.
Right. It's making me think about when I drive and I just go on autopilot and I just start going to a place that I always go. Like a friend of mine, I go to her house every week, and she moved. And every time I go to take her home, I keep going to the old house. And I'm like, oh, I did it again. And like, not even thinking about it. But it's it's just like learning to drive. Now, in the beginning, you think about everything that you have to do, right? You think about how pushing the pedal, how far do I have to push the pedal, right? And then after a while, it's automatic.
But then if you have to think about it, it's very hard. And same with riding your bike. If you have to think about that after you learn, I call it unscrambling the omelet.
Right. You mentioned proprioceptive a couple times. Can you just explain that for people that don't know what that means?
Yeah, so the sense of proprioception is a hidden sense that we have, that the brain knows everybody position and posture in space. So you know where you're, like, you have like a body map, and you know where you stand, like if you're standing, you have a pretty good idea where your wrist is, where your knees are, where your head is, that's kind of, you close your eyes and you still have a pretty good sense that your arm is up above your head, so on. That you can do with eyes closed, with eyes open. Eyes open, obviously, the visual information helps you be more accurate. If I were to say, close your eyes and point to the board, you will point, but you might not hit the letter that you intended to hit, because you're not relying on the memory of the visual memory of where that was.
Right.
But you still have your sense of proprioception, because you still know your arm is kind of in there and moves this way and so on.
Right. And is that the autistic kids have an issue with the proprioceptive, you think?
Yeah. Well, we know it because we've measured it. Yeah.
Yeah. Okay. And it sounds to me like what you're describing is apraxia, right? They're telling their body what to do and the body's not
Ap-
doing it.
Apraxia, yes, it's a motor planning issue that they're telling it what to do, and they don't have these, they have a disconnect. They don't have this for a variety of reasons. This now goes into the causality of it. What is underneath that? It's a lot of things. Could be the muscle tone,
Mhm.
the myelination, could be certainly one aspect that keeps propping up, and that now we know it's problematic in neonates that go on to develop the diagnosis of autism 3 or 4 years later, depending on where they live and where diagnosis available and so on. They have, we have found these neonates have delays in processing this sound information and sensory that comes from sound in the brainstem, which is a structure that is fundamental to serve as like an anchor, like a frame of reference for timing all the sensory information and the integration with all the motor components. And that is a problem at birth, because we found about 1.72 millisecond delay in the processing of the sound. And this is in the sound system, process a microsecond time scale. So it's a very, like it's an order of magnitude. It's like huge delay. And this delay remains unless you do something about it for years until this child gets a diagnosis. So it's a problem with the brainstem.
I know what you're talking about, because when my son was little, when he was 2 and he stopped speaking, we took him for a hearing evaluation to see if he was hearing impaired, and they did a bear test, which means they would make a sound. I think they put like something behind his ear, right? And they'd make a sound and then it would vibrate, right? And they could tell. And the results of the test were, what they told me was, there's a delay from when he hears the sound to when it registers in his brain.
Yep.
So sounds like it's exactly what you're talking about.
Yeah. So they do these now in neonates when they're born.
Mm-hmm.
And most hospitals do it at birth. And so we were able to work with the New York Institute for Basic Research, the neonatal unit, and they gave us the data from the neonates, and these were all records, but they had the data, so I was able to analyze it using a new technique that we invented in the lab. And they had already received the diagnosis. They had already, passed the 4.5, 5 years of age. So they already had a diagnosis in record, because they keep seeing the kids. The pediatricians continue to see them. And so we went back in time, we went back in the records, 100%, all the children that got the diagnosis had the delay.
Wow.
And so it's very powerful causal that we understand that if you don't have, if your temporal information is misaligned, from all the sensory processing, if you're not processing, because the other thing we found was that the bandwidth of all these sensory, the frequencies were not there. So the system is processing a slice of the sensory bandwidth, the full bandwidth of the spectrum frequencies. They're sampling from a narrow band, and so you have those two things going. The narrower sensory processing in a particular band, and the delay shifted in delay by almost 2 seconds. That's huge amount of time delay. And so, I mean, it varies from child to child. So the instrumentation that we had access to samples 3 different subregions as the wave propagates from the cochlea through the nerves all the way to the primary auditory cortex. So it goes through 7 stages. So we could see for each child, where the major delay was, so the bottleneck is happening here, it's happening here, but cumulatively, all the way when it gets to the primary auditory cortex, you have almost 2 seconds delay in a structure that at birth is ready to help support every single learning process in the somatic sensory motor domain, all the reflexive, protective reflexes, all the sequencing for motor control, all the coordination, everything is in that structure at birth. It's ready for you to go and learn and so on. So yeah, that's a huge difference. But it's hidden to the naked eye. That's the whole thing, that you don't know. I mean, you only know when you measure it at the research level that we're doing. Pediatricians don't know these, the regular pediatrician, unless you have somebody doing research, like I said, pediatrician, and also has a PhD and is doing research, like the pediatrician we collaborated with. So otherwise, it's just not gonna be in their radar.
So that's sound delay to the brain, but what is causing the delay to the physical movement? That's the apraxia. Like, what is causing that?
It could be a variety of factors, but the temporal information is critical to build those maps that compensate for the delays. Because there is a delay, a natural delay. There's a natural delay. So we all have delays. Everybody has delays, right? And they vary depending on the myelination, and on the, the muscle tone, and on the, like an athlete is way faster than, and so on. A musician, you train, so these things are trainable. But if you have issues underlying all of that, then the integration of the different delays that we all have, from sensory processing of light, of vibrations and sound, touch, pressure, movement, all of those have delays. So they take time from the time that your sensory receptor processes to the time that it travels. Just imagine it starts to travel through a cable and goes all the way to the spinal cord, and the spinal cord goes all the way to the primary sensory cortex, whether it's visual sensory cortex, auditory, sensory motor. And so that takes time. And that's what I mean by there is a natural delay. In the neurotypical case, all those get coordinated, and you go like, okay, you're going to take 500 milliseconds to get here. I'm going to take 200 milliseconds, and so on. And then you make your coordination, boom. And you have a frame of reference. You say, okay, this guy is like Central Station or Penn Station, trains coming in, going out, and you have to time it. It's exactly like that.
Yeah. Exactly.
And so now you have something in one of the senses, say the auditory, and it's coming with an intermittent random delay. You can't predict it. So how do you coordinate with the other sensors to get that on time, right? That's a problem.
Mm-hmm.
So what underneath that, what is it? It could be myelination patterns. It could be other structures, and it's going to be personalized. It's going to be individualized. It depends on what went on during neurodevelopment and what insult the system received. That usually this is compensated by, because the nervous system very resilient, very plastic, and these kids are an example of that. Where every single child, adolescent, adult that comes to my lab, it's a marvel. Like, okay, their system figured it out. They're walking, they're reaching, maybe not at the same speed, maybe not with the same coordination, but they're doing it. And part of the problem is people are not giving them enough time and enough credit for what the system has accomplished, which is a major feat. And so if you give support, if you give, you presume competence, and that's not just a cliche. This is the reality of things. You have to give it time, right? Give it time. The system's a little bit delayed, but give it time, give it the support. It's gonna catch up. But that's not happening. People are in this hurry, like, okay, it has to be done this way, and so on. Not giving enough opportunity for to work with what is already working. That's the whole philosophy in my lab, is you're gonna discover what the system is already capable of doing, what inherent capabilities it has, because those predispositions and capabilities help you build capacity for the stuff that might be delayed or different. But you have to discover what that is, and then help the other, part that is not, that is maybe underdeveloped or might be developing a different path, discover what that is. So with the digital revolution, we can do a lot because it tells us a lot that we couldn't see before. And now we can see. It's like putting on special goggles or something. So
Is
that's
there a way for you to hook them up to the wires and to test to see the delay with the apraxia?
So it's very difficult because of the hypersensitivities. So we have done this with people who tolerate it, who tolerate the wires and the sensors and the wearables and so on.
Yeah.
But over the years, what we've done instead is, and in addition to that, is develop new technologies that are unobtrusive. So like recently, there is a field called computer vision that is using AI and machine learning to develop models that you've probably seen them all over the place. Like when you travel and you go and they do biometrics and they put your face, a camera, and they say go because they already have your biometric of the face. So that technology can be used and deployed in screening and diagnosis, because a brief video gives you all the information. There are models now that you get 3D gaze, plus voice, all the grid of the face, so you can see like the ophthalmic area, the maxillar area, the mandibular area, maxillary mandibular area. So these three regions of the face are innervated by something called trigeminal nerves, which connect to the brainstem that I was telling you about, the delay. So we can see the delays in the micro movements of the face. We can see then these problems unobtrusively, just video. And we can also see the dysregulation of the heart. So the heart is very dysregulated. These kids, they're in fight or fight mode.
Yeah.
Like right now, we're running a study, thanks to the generosity of one of the moms, donated the funding to do the study, and in 55 families that we're tracking for 3 months. And they give us heart rate variability through a polar sensor that they bought in Amazon. And then we take the face, and we're establishing that correlation between elevated sympathetic drive that is keeping, having in flight or fight mode, and facial micro movements that are indicative of that, so that you don't have to wear anything eventually. We're developing that to tell when the system is in pain, because we study pain in the lab as well. It's separate from autism, just in general, chronic pain and the thresholds, the personalized threshold of pain of people. And we realize that in autism, they are by default have the same signatures of people with chronic pain or people who are in pain, induced pain, and things like that.
Really?
But that's their default. So the heart and the face have those signatures, like they are in pain, literally. Like,
wow. Is there a way to improve the apraxia in any way? I mean,
yeah,
I'm sure, I don't know that you could cure it, but you
can certainly improve it with a variety of supporting ways, including, and very importantly, these spontaneous movements that help them then transition to more organized voluntary movements. And we've done it experimentally, in the context of like a school. We went to a school, recorded 25 non-speakers way back in 2011 or so. And we saw the improvements, like how we were able to make their movements predictable. Like their voluntary movements were totally random. We make them predictable. They were very noisy. We dampened the noise. And so they began to have a more certainty in their prediction. The timings then aligned. They had synergies that were timely. And so that improved what they intended to do, match it to what actually they did. And so that, in that sense, it improved the apraxia significantly.
like, what kind of intentional movements did you do?
These were, so we started out with simple pointing movements to a target on the screen, and we had 2 choices. that they had to make to match. They had in the center of the screen, they had a little stimulus, visual stimulus, like something simple, like a circle in red, and then you had a red circle and a blue circle, and it's like, which one is it? And then, so they would go to the red. And then we would increase the level of complexity. So we would put there a circle in black and an ellipsoid. So you have a circle and ellipsoid. Those are tricky, right? Because they look similar, but they would go to the ellipsoid if it was an ellipsoid, or to the circle if it was an ellipsoid. And then three-dimensional objects rotated, like a banana, and then a banana matching that, and then rotated banana. And they would go and say, no, that, and so on. So that we started like that. And then we did a something more gamified, which was, since they were wearing sensors, right? We built like an invisible grid in the space in front of them, which is called the peripersonal space, which is the space where we reach like maximally, like that's our bubble of peripersonal space in front of us and above. We had that grid, and we planted in that grid points that this is we in the computer, right? They don't know this. That if their hand passed through that point, like say there's a point here, and the hand passes close to it, it would trigger a movie or music or something they like the parents. We worked with the parents, and they told us they like these and that, you know, like this movie, and we would play a clip.
Okay.
So now imagine that you're sitting there and you go like that, and you play a clip of The Little Mermaid, that is your favorite movie. And you're like, wow, what was that, right? So they would try again and see. They were very curious kids, you know, one after another, 25 non-speakers. And they would just, I had the movies. It's like, it was amazing. And then they would trigger, and then they would hold their hand there, like on top of that, just to watch the whole clip. So we played with that. It was gamified, but it gave them a sense of agency, because a sense of true autonomy of their actions. So they match what they want. They learn to match what they wanted, their intention, which was to find the magic spot that plays The Little Mermaid.
Yeah.
To the posture that did that, and they did it themselves. I didn't have to tell them, go put your arm there. They did it themselves, and that sense of autonomy was very important. And that itself dampen the noise and make them more predictable. So systematically, they learn how to match, how to navigate, how to map the space.
Right. This all reminds me of like learning how to play the piano, right? It's and you have to learn where your fingers need to go, and you know, and it takes a lot of thought, just like driving and riding a bike, right? In the beginning, you have to think about it, but as you do it over the years, it just becomes automatic. You don't have to think about it.
That's right. Yeah.
So talk about spelling or RPM. So this sounds like what you're doing is getting them ready to learn how to point at a letterboard.
Right. Yeah, all of these. And one thing I think that that my lab could be very helpful to all these methods that are trying to teach the kids how to spell and how to type and how to all of that. This is the very basic foundation of it all. Like you understanding, breaking it down. I was talking to Renee Hayes, the mom of Matty Hayes. I don't know if you know him. He's a typer, and he's an emerging speaker as well now. Mm-hmm. He types beautiful things. We've gotten into these very deep conversations, and it's amazing like how interactive this can be, and how eloquent and enlightening this fellow is. And we've been talking about like how we could help speed up the process of acquiring the typing skills and so on, beyond the meaning of the letters. No, not there yet. We're not there yet. Okay, just acquiring the foundation of motor control, right? Because I've modeled this all the way from the beginning, right? And I've studied in infants and in adults who lose it, in Parkinson or in differentiation or in essential tremor. And so that's where my lab could be extremely helpful in building that foundation step by step, dissecting this problem into its very basic components. We know we have the mathematics, the geometry, dynamics. I mean, it's like we have the elements to do this very methodically, but it needs to be done because I think a lot is expected from these kids at the beginning. And it's like, we gotta start slow. We gotta start from the beginning, before getting into these whole phrases, entire phrases of language and so on. Before getting there, get the foundation so that they get independent. They become as independent as they can. And some might not, some might need the support, the physical support, and that's fine. But you need to, at the very least, try to build that independence, because we did it with 25 non-speakers who had a lot of apraxia and a lot of issues, and we saw them on their own acquire that autonomy and move the arm and sustain it and so on. So it's doable, but we're gonna have to do it slowly and little by little, collaboratively. I mean,
Yeah, because my son, I don't know if you know, he's passed away at this point, but he was, severe. And I look at the spelling and I don't think that he would have had the ability to just sit down the first lesson and just start pushing a pencil through. I don't think he would have understood, but he loved The Little Mermaid. And hearing what you're talking about, that he would have learned, that he would have done. And I feel like if we broke it down that way for him to start learning how to point, and he'd get rewarded by the clip of The Little Mermaid, I think he would start to get it. And eventually we would be able to work up to the point where you could start teaching him the letters and all of that. So
I think so, because the reward, and this is a fundamental departure from like the behavioral reward. The behavioral reward is something external that the person gives you when you accomplish what they want you to accomplish.
Right.
This is not it. This is not it. This is a reward that is intrinsically self-motivated by the person itself, that gets a reward from what it did. The system gets it. And that's the autonomy.
Mm-hmm.
That is the part that is missing in the behavioral approach. Behavioral approach.
Right. I was going to say, it's not ABA. It's not do this and you get a reward.
No.
Right. It's their own movement. It's
their
not
own movement
telling
is the
them.
reward. Their own movement outcome is the reward. And that is a very powerful form of agency, and establishes the sensation of body ownership, which is a sensation that we don't come with it. This is not something we come equipped with. We have to learn it. So as a baby, you start mapping your body. You rock your body, so pressure, you roll, you discover anti-gravity movements, and eventually you say, I did this, I intended to do this, and I did this, it has this result. And you do it again, and this is my hand doing it. And that is an emergent thing. It's not, you're not born with it. You have to learn it. In fact, you could lose it due to a stroke or a brain injury. That sense of intentionality, you can lose that, and then your hand can become what we call alien hand syndrome. I don't know if you've ever heard of this.
No, think so.
It's a syndrome where the person, through a stroke or through a lesion to the corpus callosum or some problem, loses the map between the intent to move and the action, the motor program realizing that intent, and they could grab their, choke or pull their hair or grab the other hand. And it's very disturbing. So they ask actually the neurologist to amputate the hand because they don't recognize it as their own.
Yeah.
So body ownership, which comes through action ownership, and through that loop between the mental intent and the physical intent, is very important to build a sense of self. And that is a foundation to then understand others that move like you, to interact with them, to time their movements, and so on. So it's a very important sense, and it can be established, but it's not a given.
So you're just making me think now with they don't recognize what their own hands do. some of the kids will have behaviors where they attack other people, or property destruction, things like that, and then they'll type later, I didn't want to do that, my body just did it. Or the eloping, they're like, my body just takes over and it just does it, and I didn't want to do that. I mean, how do you explain that?
Yeah, well, I mean, you have the impulsivity, right, which we typically override and don't let it happen, but it's there, right? Because sometimes you're arguing with somebody on a point, whatever that is, and you want to just punch that person in the face, but you have
True.
you do, but you dampen that, you
Right.
override that impulse. But
Mhm.
in your system, because just as important to facilitate the movement, there is a system that inhibits the movement. And if that system is not talking to the other systems,
Right.
you might not inhibit. So you just go. Look at Tourette's, right? A lot of kids with Tourette's, they do entire motions, right? Complex motions. These are motor programs that get deployed rather than inhibited.
Right.
All right. And so that's a problem. And that's part of the alien hand syndrome and so on. You deploy entire complex motor programs that are not beneath your awareness. You didn't intend to do that, but they just were deployed.
Yeah. So do you work directly with any spellers? I mean, are you connected with Elizabeth Bonker? Did I see something?
Yeah. We're so
Communication for All.
Mm-hmm. Yeah, Elizabeth and Jeannie, Reem, her mom, and I are, and my postdoctoral fellow Dr. Mona El Sayed, we put together a study that is ongoing. This is a study I was referring to, and it was funded by the Hildebrand family, and thanks to them for their generosity, and at my end by the Nancy Lou Marks Family Foundation that is funding us to also do this. And this is a 3-month study where we collect data 3 times a week, and during before and after different activities that are relaxing or a brisk walk, or things like that. And we're collecting the face and the heart, and they're doing it at home. This is completely, we train the families and they're doing it themselves. It's really participant centered research all over the US. We got people from all over the place. And it's not I'm in New Jersey, but it's not a New Jersey studies. It's nationwide, and we'll see. I mean, we're presenting the results in the MAPS conference in March.
Okay.
So we're very excited about it, because if we find this proxy of the sympathetic override, the overloaded system with flight or fight mode and we find it in the face, which we are already having evidence that this is going to be possible. Then a simple app can tell you you're in this regulated mode, and guess what? When you're doing your intervention, whatever that may be, or you're just at home, you can then try to relax and reset your system, because you don't need to be in flight or fight mode to do anything. That's really not fun. And so at the very least, we can identify it, and we can suggest we're doing different things that people already do at home, relaxing or sensory deprivations to just like dampen the noise, or walking or yoga, whatever it is that people do. Just try to identify what makes you calm, like what relaxes you, what makes you go back to the state of relaxation, because otherwise in flight or fight mode, it's just very difficult to function for anybody. So so that's a study we're doing with Elizabeth Bonker and Jeannie Green. We call it regulation for all. Like she has communication for all, so we came up with this regulation for all, so that as part of a routine you can get regulated.
Okay. Yeah. And you need to be regulated in order to spell, right? And even the person that works with them as their communication partner needs to be regulated.
Needs to be
also.
regulated and needs to, so now we're doing the study because we, the budget was limited and so on, and it's complex, and we want to first go step by step again. So now we're doing the study center at the child, right? Or the adolescent, the person, or the young adult. But ideally what we want to do is get both the partner and the person, because then we can see what states regulate each other, right?
Mm-hmm. Yeah, because a lot of parents have trouble working with their kids,
Yeah.
and the kids will not spell with their parent. And I always want to tell the parents, and I don't because I control that, right?
Yeah.
That you're not regulated. You're too nervous. You're too
Yeah.
excited. You need to calm yourself,
Yeah.
before you work with the kid, because they're picking up on that, and it's
Yeah.
making them more nervous.
Yeah, it's an automatic mimicry. We've
Mm,
seen it, and it is just the natural state of how social and emotional movements work. When we are with each other, we entrain. This is all beneath awareness. We entrain with each other. We tend to sway together. We tend to do gestures, micro gestures together, because we do mimicry, and that's natural. And
yes.
so they will be automatically mimicking their kid.
Yes.
If their kid is dysregulated, they will automatically get dysregulated just to even build that rapport that they do all day long
Yes.
with them. So absolutely right. Yeah. And
Yes.
they need to be neutral in order to do this. It's difficult. It's easier said than
Yes.
done.
Yes. It's funny you say the mimicry, because I've caught myself doing that. If I see a mom that's rocking a baby, I catch myself rocking.
Yeah.
I don't even realize it.
It's a very human thing.
Yeah.
Empathize with the other. We all do it. Oh, everybody does. People in the spectrum do it. All these people,
Yeah.
all these,
Well, especially kids on the spectrum, they're hypersensitive.
very much so. All these false notions that they don't have empathy, or that they don't.
Oh, no, it's the
It is
opposite.
the opposite, way out there, the opposite. But you have to measure it in order to see it, or live with them to sense it yourself,
Yes.
experience
Right.
it. But you have all these researchers that I call them, they live in the ivory tower,
Mhm.
never really interacted with people for real, like, in like we do,
Right.
and are coming up with all these theories. And then I look at the research,
Hmm.
and I said, "What? How did they come up with that? Like, what the hell did they measure to say that?"
Right.
All right, so they're measuring, for example, how long it takes for the person to look left versus to look right, and they're like manualizing this by hand.
Hmm.
That's their measure.
Mm.
And I'm like, "You're kidding me. You're
Mhm.
kidding me." Because you have built a theory that has destroyed an entire generation
Yeah.
based on nothing.
Right.
No, this is wrong. This is so wrong. I mean, I'm total dead against that.
Yeah.
And I'm not, I'm persona non grata in those spheres, you can imagine, but it's all right. I've been able to survive, no problem.
In the spelling world, ASHA had, put out a statement about spelling, saying that it's not real and everything. So now people want to scientifically prove that it is real. And I would guess that Elizabeth Bunker would be one of the people on board with that, with wanting to make sure that that the science is behind it. It sounds like that's what she's doing. I'm not sure. Is there anything that you can do to help that front, or no?
Well, first of all, I think that there hasn't been any, there hasn't been resources to support this question, to actually support research towards that end. The resources come from the parents themselves,
Mhm.
and from private foundations, like the federal government and the state government they haven't given any resources for non-speakers, or towards developing an educational program for non-speakers. So there's a lot of improvisation out there because of that. And there is a lot of, people coming up with ideas of testing this or testing that. I am not against testing, whatever. And we do very rigorous research in the lab, and very mathematical, and we just do it very systematic and reproducible, so we aim for finding results that are reproducible by others.
Mm-hmm.
So we're totally on board with doing the applying scientific method to this. What I'm not for at all is questioning, it's beginning this question by questioning the authenticity of what somebody is doing or not doing.
Mm-hmm.
I don't agree with that.
Mm-hmm.
I think we have to start from the very basic motor control question that I was discussing at the beginning of the interview, and see, what foundation is there to help this kid to support this motor system, this somatic sensory motor system, regulate the person and so forth. And then we can do more advanced research on language development. What kind of language development? It's not going to be the language that we develop. It's different.
Mm-hmm.
What mechanisms lead them to communicate, like the way Lisa Bunker does, or Matty Heiss, that I talk to him and he types, and then he's talking, he's reading and talking what he's typing and stuff like that. So how is that emerging? How is that process? Because it's not the way that we learned. We learn a different path, completely different from this. And so I'm curious about that, but I wouldn't go into this research questioning anybody's validity of what they're doing. That's not my interest. I understand that they will get there, eventually they will get there. I just want to start from the very basic beginning and get there together.
Right. And what is your goal? What do you want to achieve?
I want to model an autonomous agent that does this, an autonomous artificial agent that does this. And that's my research, the basic science goal. Like, I want to build a robot that is autonomous for real. Not what we have right now is not that.
Mm-hmm.
So I like that for assisted living and for other things like this will be good. I want to understand the notion of autonomous intelligence, creative thinking. How do we get there? That's the basic science question. Now, the practical question is different. It's like, how do we help these kids? How do we, in the practical society that we live, how do we get insurance coverage for them, so that they get covered to do these therapies, to do this, because the spelling to communicate and the rapid prompting and all of these different methods are therapeutic. We can see that they get calmer, that they can get better. So they have a therapeutic, when done well, they have a therapeutic element to them. So how do we further understand that? And how do we get the system to incorporate that in the education system so that they receive a formal education that is tailored to their capacities and to their needs, right? That's my other goal. So I have in the lab two different goals, right? One is basic scientific goal, this fundamental question: how are we such creative thinkers? How do we do this autonomous intelligence thing, that we are problem solvers? How do we do that? All the way, like with equations. I want to get the equations that unfold that. But this is different. This is the day-to-day living in a society. And it's different in the US than in Europe, than in Africa, than in Australia. So it's different. So I live in the US. How do we help these kids get insurance coverage and get an education that is appropriate for what they know how to do, and how do we get the proper support? Like ABA got into the schools by mandate and all that, and how do we get this for all these other, how do we get there? So
Mm-hmm.
That's the goal. How do we get there? Because clearly ABA doesn't work for them. So we need an alternative method, and there are all these methods, but they need to be infused with the science and the technology that will accelerate the process of learning. So instead of taking you 3 years, it will take you, a year, or whatever, whatever it takes you, but we would accelerate it and we would reproduce it. So other kids that come in the queue have a plan, and this is step 1, step 2, step 3, and we reproduce it, and we get the science out of it. That's my goal. And this is a very important goal in my lab, and everybody who joins my lab, thank God, joins that goal. So we do the basic science. If people out there read our papers, they see that they're very complicated and whatnot. That's the basic science. But we do all this other stuff for service and community-driven research, and a lot of volunteering our time for it. And it's towards this goal, this general goal, like the day-to-day life.
That sounds good to me. How, if somebody has questions for you, they want to get in contact with you, how would you like them to do that? Do you have a website or an email? How would
We
you like
we have a website. I have email. My work email, ebtorres@psych.rutgers.edu. Yeah, so I mean, we work with parents and nonprofit organizations in the area. They work with legislators. They're trying to make them aware of our research. It's an uphill battle because, ABA gets on the way, but I'm trying to make friends with ABA to, like, you guys need to come up to the 21st century. You're working back in the 50s under a model that is not only outdated, it was never meant for humans.
Right. Yeah, right.
This came straight out of animal conditioning, and I wouldn't even do that to my animals, to my dogs and whatnot. It's like,
yes, that's exactly what it is. I remember when my son was little and he was in school, and I went to SeaWorld or something and watched them say, do this, and they tossed him at fish, and I was like, oh my God, that's what they do with my son.
That's what they do. And they kill any chance for.
But isn't that that's creating an automatic response?
But it's not autonomous. Automatic isn't the same as autonomous.
Right.
Automatic, when I reward you from the external thing, creates a codependence.
Yes.
Right? And so you're never really independent.
No.
You're not autonomous.
No, and let me tell you something. My son, I watched when he became an adult, he did nothing on his own. He waited to be told what to do. He waited to be told to go to the bathroom, told to wash his hands. He waited to be told to do everything. And what happens is they turn 21 and now they're expected to live independently.
Yeah.
Or even in a group, if he went into a group home, they expect them to be independent in a group home. And I said, well, how's he supposed to be independent when he was taught to be told what to do all the time?
Yeah, but you know what it is? In my opinion, kindness and common sense. Kindness and common sense.
Yeah.
You wouldn't do half of the stuff I see they do to the kids. You wouldn't do it to yourself.
Right.
And that's the first question that they need to question themselves, right?
Yeah. Yeah.
Are you doing this? Would you do it yourself? Like, would you go 3 hours a week pointing to red for a sugary treat? Do it. Go ahead and do it.
Mm-hmm.
Right? That's my question. Like, to all of these people, like, how would you feel another human being doing this to you, controlling you 24/7 like that? It's all about control. It's all about control.
All right, I have to wrap it up because I have to go. I have to get somewhere. So, but I just want to thank you very much for taking time out. I know that you're very busy and you're doing meetings all the time, but I want to thank you for taking time out to talk to me today. I appreciate it very much.
Likewise.
It was very nice to meet you.
Anytime. Very nice to meet you.
Okay, thank you. All right, bye-bye. That's it for today's episode. I hope you enjoyed listening and it helped you gain a new perspective. To learn more about our children's book series, Robbie's World and His Spectrum of Adventures, or to learn more about what we do at Robbie's World Foundation, simply visit our website at robbiesworldbook.com.
Thank you for joining us today. Be sure to join us again on our next episode of Spectrum Perspectives.